So today we're going to perform two triaxial tests, both compression tests on dry sand. We're going to build or reconstitute those specimens to two different densities, as loose as we can, and then as dense as we can for the given sand that we're going to test, because we want to see how the behavior, the friction angles that we measure, and also just the mode of deformation depend on the density of the material. It's sort of an unusual triaxial test system. Usually when we test triaxial specimens, we have them placed inside a chamber that we can pressurize around the outside of the cylindrical specimen. But in this case today, we're actually going to provide that confinement by putting vacuum on the inside. So we're going to have an air pressure or pore pressure U that's actually negative relative to the lab pressure. So that negative U is going to provide our effective confining stress, sigma 3 prime. Okay? And then once we build it, we're going to put it into a deformation controlled testing frame, which is going to slowly squeeze it vertically. And so we want to measure, of course, that sigma 3 from the vacuum acts in all directions. It's an isotropic stress, so the vacuum acts both vertically and horizontally. But in addition, when we go to compress it, we're going to be measuring a deviator load. We're going to have a load cell that's going to show us how much extra force it takes to squeeze the sample. And so we're going to convert that to a deviatoric stress, sigma deviator equals sigma 1 minus sigma 3, by knowing the sample area. And then we're also going to measure the axial deformation. As we squeeze the sample, it's going to get a little bit shorter by some delta H. And we can, of course, relate that to an axial strain dividing by the initial height of the specimen. So let's get started. So we're going to build this vacuum triaxial specimen on a special base plate that has a sample cap attached to it. And you can see there's a small porous stone here that's sintered bronze. It has a tube connected to it, and so that's connected to the inside of the specimen. And through that tube we can apply the vacuum confinement after we've built it. We're going to build the specimen itself inside a split mold, which is aluminum and a rigid mold, except it also has this porous lining in it, which allows us to also provide a vacuum to the outside of the membrane that we're going to use to keep the membrane nice and tight around the mold and produce a nice cylindrical sample. So the first thing we're going to do is take the latex membrane, which is 0.3 millimeters in thickness, and we're going to connect that to the bottom cap, and it needs to be sealed because we need to maintain a pressure difference of whatever vacuum confinement we decide to apply during the shearing. So in order to seal it there, we're going to take some O-rings and squeeze the membrane tight around the cap. And then we'll put the mold over the membrane and bolt the two halves of it together so we have a nice tight sealed system, and we'll be ready to go. Okay, so we've assembled the split mold and tightened the bolts so we have a good seal hopefully around that. We've connected this blue tube, which is attached to the mold, to the liner, to a vacuum source. So when we stretch the membrane up and over the edge, we get a seal there, and the vacuum then pulls the membrane out nice and tight against the walls of the mold, so we have a good cylindrical shape in which to build the specimen. So we're going to build the loose specimen first, and just like we did with the permeability testing, to build a loose sand specimen, we're going to use the zero fall height fluviation. So we have a cylinder with a screen at the bottom that the sand can pass through, and we put that screen all the way down to the bottom. So as we fill this cylinder up, doesn't really matter what density it's going to be. We're going to very gradually then let the soil flow through the screen at the bottom as we pull it up and deposit the soil with very low energy. So I'm going to fill up the fluviator first. This is Monterey 30 sand again, just as we tested with permeability. It was also in our first lab. Whoa, right there at the top. I'm going to start the lifting here. We'll reuse exactly the same mass of sand, same grains in fact, to run the second specimen, the higher density specimen, when we build that in a little bit after we test this one. Alright, so there's our specimen, and we want to flatten out the surface a little bit. So when we put the top cap on, it's nice and level. We might be densifying the soil at the top here very slightly, but the soil near the top cap and the bottom cap really are protected from shearing by the fact that there's a rigid cap there, so might throw our densities off very slightly, but not a whole lot. So we have a cap that does not have a drain line in it, so we don't have to worry about having a separate tube coming off of that. We're just going to be applying the vacuum through the bottom of the specimens. And here's our top cap. And we want to make sure that that's parallel to the bottom cap. So we're going to put a bubble level down here. And of course the table's not perfectly level, so we don't want it to be level in the gravitational field. We want it to be just as unlevel as the bottom cap is. So that's what we're going to track here. And again, not vibration, but just some gentle shaping of that top surface to get the top cap parallel with the bottom cap. Great. All right. So now we want to actually seal the specimen. So I'm going to hold down firmly while we heel the membrane up. And then we're going to roll up this second O-ring to seal the system. And now we have a second tube. This one is coming out of the base plate. Through that drain line in the base cap, we're going to connect that to the vacuum source, and then we'll be able to disconnect the mold. So we've connected the second vacuum now, the one that goes to the inside. So let's turn the system so you can see that. So this is the fine tube here. That's the one that goes up into the bottom of the base cap and connects to the inside of the specimen itself. The blue tube is the one that is holding the membrane out against the mold, and we don't need that anymore as long as we have vacuum in the specimen. So we're going to disconnect that line, and we're going to disassemble the mold. So we take the split mold apart. Do we have a nice specimen? Ah, we do. Lovely. Okay, so there's our cylindrical low density specimen for the first test. And there's a few parameters we want. We know the mass of the sand that we put in, so that's important. We also, though, need to measure this volume. And to do that, we need to measure the diameter. Right? And to do that, we're going to use something called a pi tape. PI. It's a clever little device. That's a vernier scale with a factor of pi, 3.14159, etc., built into it. So when you wrap it around something that's roughly cylindrical, you can read the equivalent diameter of whatever you're wrapped around if it was a circle, right? It's basically measuring the perimeter and dividing by pi. And I can measure that to the nearest thousandth of an inch with this because it has a vernier scale. So I'm going to check the top. I'm going to check in the middle. Yeah, good. We built this in a rigid mold, so it shouldn't be too surprising, but especially with a loose sample, when we apply that vacuum, it does get a little bit smaller than it was when we initially built it in the mold. So, and of course, this is the diameter around the system, which is the sand plus the membrane. And so if I want the diameter of the sand specimen, I have to take the measured diameter and subtract 2 times the thickness of the membrane. The membrane thickness is 0.3 millimeters, as I mentioned before. And then we also need to measure the specimen height. And so to do that, we're going to use a dial gauge system, right? We could hold a ruler up next to the system, next to the sample, right, and try to eyeball what the height is between the caps of the system, but we're actually going to get a much more precise value if we use a dial gauge that can read to the nearest hundredth of a millimeter. So what we can do is, of course, this dial gauge is just positioned arbitrarily, right? So the reading itself doesn't tell us what the height of the specimen is. But if we take a reading with the specimen in there and we compare that with a reading we took earlier where there was no sand in place. So in place of the sand, we had a standard specimen of a known precise height between the same caps in the same system with the dial gauge in the same place. Then we can just adjust, right, the height. The specimen height is going to be this value adjusted by the difference in the 2 dial gauge readings. And so that's what we'll do for this specimen. So what is that? 4, 8. And it looks pretty level. That's good. See how the height isn't moving as I move it around. So it doesn't seem to be tipped or slanted relative to the base cap. So I think we're about ready to put the sample on the testing frame and run the compression test. So we've placed the loose triaxial specimen here in the loading frame, and on top of the top cap we're actually going to put a second cap of the same diameter that has a divot in the center of it for this ball bearing. And that ball bearing is going to seat in a depression here in the load cell. So we want to make sure that that's centered. And I can do that with this wheel. Bring it up close. Make sure this is in the right place. I'm going to leave a small space so there's no contact between the system and the sample. So when we start the machine, actually we'll have a little bit of data in the data file that we acquire with the computer where the table will be moving, but we won't be measuring any new load because there's still a gap in there. In order to measure the displacements, we're going to put in an LVDT, a linear variable differential transformer, and that's going to fit in right here. That consists of a housing on the outside and a removable core, and it's a magnetic system, so there's high frequency coils, high frequency signal in coils within that housing, and so depending on where the magnetic core is, we get a different DC voltage out of it. We want to make sure that's in a good starting position there. I'm going to switch this over to a fine system and look okay there. I think we're ready to run. So the table is going to move up at a rate of 0.1 inches per minute, which is relatively quick for a soil strength test, but that's good for what we want. We don't have any water in the pores that need to drain out of the specimen or need to equilibrate in terms of pressure or anything like that. In fact, we're not even measuring the vacuum with the computer. We just need to note what that is. Yeah, it's still about a half an atmosphere. I'll calculate what it is and put it on the data sheet based on the gauge we have. So let's get it started. Turn the machine on. And then we don't have the table moving yet, but very soon. We want to watch mostly the deformed shape as we move along here. Okay. So the table's now moving up, and we still don't have contact. You can tell because the ball's able to move, right? So these first initial readings in the data file don't correspond to strain. We don't calculate strain as starting until we have contact in the system and we're getting deviatoric stresses due to this deviatoric load, right? Now we have contact. So we're rolling and acquiring data twice per second. We're measuring again the deviatoric load and the LVDT. Since this test is going to go on for about 10 minutes, I'm not going to film the whole thing, but we'll shut it down for now and bring it back when you can see the deformed shape. We're now at about 5% axial strain. The loads are still going up, although not as fast as they were. And we can see finally some deformations in the shape of the sample. We can see some bulging. You can see that the diameter, especially toward the center of the sample, is getting larger, right? And that makes sense. As we squeeze something vertically, there might be some volume change, but even if there is, there's going to be a tendency for the sample to get wider. And we're going to actually need to account for that when we calculate what the deviatoric stresses are, because those stresses are based on the vertical load and of course what the cross-sectional area is. And so that's changing as the test goes on, so we'll need to account for that. We'll take it further to failure. So now we're beyond 10% strain, which is quite a large strain. Traxial assumptions about traxial tests start to break down at large strains. As you can see, even though this bulging is continuing through the center part of the sample, it's not really happening right at the caps, at the top cap or the bottom cap. That's because those zones are sort of protected. Again, they have a rigid cap right adjacent to them, so shear planes can't pass through them. So the bulging is confined mostly to the center. When we do calculate a new area for the specimen, we're actually going to be assuming that it's deforming as a right circular cylinder, but you can see from this test that that's becomes a worse and worse assumption at very large strains. You can also see perhaps that the top cap is tipping somewhat, so we're getting some moments in there apparently, or tendency for moments. So we're going to call the end of this test pretty soon, and we'll take this apart and rebuild and see how a dense sample behaves differently than this. So when we want to prepare the dense or high density specimen, we're going to start the same way. We have the same equipment. The mold is sealed, or not sealed, but placed around the membrane, around the bottom cap. The membrane is sealed to the bottom cap. We've tightened up the bolts, so we think we have a nice seal. The blue vacuum line to the mold is reattached to the vacuum supply, and you can see we have a nice cylindrical fit there. The membrane is being pulled out tightly against the inside of the mold. But now, instead of building a low density fragile sample, we want to build a specimen that's as dense as we can within reason. So we're going to not worry about vibrations, and in fact we're going to apply a lot of vibrations. So we're going to build this specimen in a series of layers or lifts, and perhaps 5 or so, and we're going to just add some of the sand. It's falling from a large height now, and that's automatically going to make it a little bit denser. But then we're also going to apply some intense vibration. We want to apply it uniformly all around the specimen, with the idea that these vibrations allow the sand grains to rearrange. Gravity is pulling them down all the time, right? But if we shake them around a little bit, they're going to fall into denser configurations. And so we're going to do that 5 times to fill up the mold, getting about 20% of the sand each time. All the soil is in and tamped, vibrated heavily. I've got the top cap in and leveled again with the bubble level. So we're ready to seal the system again and proceed with the dense triaxial compression test. As long as when we take the mold off, we have a nice cylindrical sample. I have less top cap to work with. The sample's shorter than the last one, right? Because it's denser. So I need to make sure I plug in the specimen vacuum first. All right. Should be good to go. Then we'll move it over to the frame. So the dense specimen is in place on the frame. We have the extra top cap there with the ball bearing between the cap and the load cell. By the way, that ball bearing is there intentionally to prevent the transfer of moment from the load cell through to the specimen, right? If we had a flat load cell pushing against a flat cap, we could have moments in there that we wouldn't know about because the load cell's made to not measure those, right? But this allows the top cap to rotate if there's a tendency to develop moments. And certainly the rotation isn't something we want to see, but at least if there's that tendency, then we see that it's happening. Whereas we wouldn't know otherwise. The LVDT is in place, but it's not at a good value. We want to leave plenty of range for it to move, be recorded. All right, and we're going to start this. It's going to deform at the same rate, so again 0.1 inches per minute, and we should see a different sort of deformation, right? In a dense sand, it's at the same confining stress, but it's much denser. So when it goes to shear, instead of contracting and becoming denser and therefore moving the failure to some other plane in the specimen, failure should result in dilation, right, in a dense specimen. So we should see a pretty different sort of mode of deformation in the sample, and also you'll see that hopefully in the data file that you're going to process from the testing. So here we go. Turn this on. So the motor's running, but the table's not moving yet. So make sure we start the acquisition. And we'll start the table. Alright, there we go. Again, there still is not contact, so our early data readings are going to be without significant load. But then when we get contact and you see a departure in load from the initial flat value, that signifies the beginning of the test. That's the LVDT reading from which you calculate zero strain. And we have contact, we're rolling. So here we go. Again, this takes about 10 minutes, so I'm going to pause the camera and we'll turn it back on when things get interesting. Zoomed in a little bit here, still in the early stages of the test, but just to note, the loads are going up more quickly, and this isn't surprising, right? The denser soil is more stiff, has a higher modulus, but it's bulging, you can see, kind of slightly, much like the loose specimen did in the early stages of the test. So we want to note that for sure. Okay, so we've exceeded the peak load. The load has actually been dropping now for a little bit, and we can start to see why. We have a different mode of deformation happening, and usually this happens in a direction that we can't see very well from where the audience or the camera is looking, but this one's beautiful. You can see a ridge here developing in the surface of the soil, right? There's a bulge and then a sharp ridge at an angle that goes up there, right? So we have a distinct localization of the shear. So all the deformation that's happening now isn't happening uniformly across the height of the specimen. It's all happening in this localized diagonal zone, and that's because the soil here is denser, the soil down here is denser, and the soil within that localized zone dilated when it sheared, and so now it's the loosest plane in the sample. And of course, if it's the loosest, it's going to be the weakest, and so that soil continues to shear, may continue to dilate as you get out to large strains. So this is a really great example of localization shear plane failure in a dense granular material. So we're well past failure now, and of course at this point the additional deformations don't really tell us what the strain is very well, because it's not, we can't normalize it by the height of the specimen anymore. Somehow we should normalize it perhaps by the width of that zone, but that's pretty complicated, so we don't usually do that. We just recognize that once we see this localization, we're at failure. We can track the loads as they drop down, often to some residual value, and hopefully we'll see that in your data file as well. You'll have a peak, and then you'll have sort of a larger deformation plateau. But this is the dense response that's so different than a contractive material of the same soil at the same confining stress, right? So, excellent.